Well, go ahead, Anna Maria, if you want.
Perfect. So, okay, welcome to the last lecture of today's. We have the great pleasure to have Chris Monroe giving the lecture. Chris is our expert in trap ions. He was before in University of Maryland, and very recently he moved to Duke. Chris has a fantastic experimental system, and he's even having a company. He's owning his own company now. Chris, it's great honor for us to have you as a speaker of our Boulder Summer School. So thank you very much for accepting our invitation, and please go ahead.
Okay, thank you, Anna Maria and Leo and Caden, and forgetting the last organizer.
Ian Spillman.
Oh, again, yeah, Ian, of course, my closest colleague. So yeah, thank you for having me. I guess this was supposed to be last summer, is that right? It got put off, and
yeah.
Okay, sorry about that. Sorry, I'm not there in person. I love Boulder. Spent 15 years of my life in Boulder, but I'll be back sometime. So I guess I'll have 3 lectures this week, each, I guess, 90 minutes. And so nice. What's nice about that, there's plenty of time to go slow. And what's also nice is that you should anybody interrupt me at any time, and because we can sort of take it at a slower pace. And I want to make sure everything is conveyed. I am going to show some kind of pretty pictures early on for the first few minutes, very kind of broad introduction to the field of quantum computing and quantum simulation. And then I will narrow it down today to talking about these individual atoms and our pretty high level of control at the single atomic level and what we plan to do with them. So unlike most of the lectures in this course, I am going to talk a lot about quantum computing, quantum gates, even some algorithms. I am going to try to, in the later lectures, talk about quantum simulation as it relates to many body physics problems. They're different sides of the same coin, actually, and that's what makes the field lots of fun, I think. And as Anna Maria mentioned, I'm recently arrived at Duke University, although most of my group is still up in Maryland, and we're on our way down. So I'll talk, almost all of any data and so forth will have come from Maryland, but we're setting up a quantum center at Duke that will be a user facility for advanced quantum computers. And I'll tell you kind of what that means, probably in the last lecture. And toward the last lecture, I'll talk a little bit about what IonQ is doing in this field. And as like any company, they're doing things that universities might not be able to do very well. And in this field, what that means is that their quantum computing systems won't be as flexible. So they might not be as interesting for research in the way that we can do at the university. However, because their systems are not so flexible, they will be very high performing. So, there will be science and so forth. For me, it's been very interesting because I don't run the company. I'm not really an operator there. But I oversee the scientific vision there and help them design their latest systems. So it's a lot of fun seeing, all the sides of the coin in this field. Okay, so let's get started. So quantum computing and quantum information science in general I think it's so fun to talk about at a high level because it's based on you could argue in the 20th century that information theory and quantum theory were really 2 of the standout advents in the last century. And in a sense, quantum information combines them. So, of course, you are all students of physics. You've had your quantum. So that's not really, for many audiences, it's the quantum that's the more exotic part. But if you haven't read up on your information theory, there's a wonderful paper by Claude Shannon, very famous in 1948, where he basically invented information theory and defined the term, the binary digit, the bit, the fundamental unit of information, 0 or 1. And of course, around the same time, maybe slightly earlier, Turing devised an abstract machine that could compute. And in fact, it's a universal machine called a Turing machine, where you have a bunch of bits on a memory, and this tape might move with respect to a head, or the head moves, it doesn't really matter. But the head has memory, and it allows you to interact with the tape and maybe flip bits depending on the state of that bit and do logic gates. And that is a model that's a universal model for all computing. And so it was very important. I think these two men really showed that information is abstract. It's not tied to any one type of hardware, and it's related to bits fundamentally. If you can find a bit in nature, you can build a computer out of it, basically. And so that abstraction in the mid-20th century was really important, I think. And we're seeing it play now in quantum computing because, quantum bits, you've heard the term, they're hard to make and control. But the good thing is it doesn't matter what your quantum bit comes from, as long as it behaves quantum mechanically, you can build a quantum computer from it. As students of physics, one other aspect of quantum information that's fascinating to me, and it can be subtle, is the concept. Well, I showed this equation here. This equation, that's not a Hamiltonian. That's called the Shannon entropy. For some reason, it has H. I'm not sure why. Maybe that stands for Hamming. I'm not sure. But it's the information entropy for an alphabet with probability distribution of k letters p sub I. And it's sum of p log p. And when you took statistical mechanics, you encountered this probably more in the context of thermodynamic entropy, statistical mechanical entropy. And so we usually use the term S in physics for entropy, and we often put a Boltzmann constant in front, but it's the same idea. And in fact, one of the Feynman lectures, this is not one of his physics lectures, his 3-volume set, it's a separate one called the Lectures on Computation. He has a chapter which is basically on the single atom ideal gas, which seems a little strange because an ideal gas means that you have lots of atoms that don't interact, but you can define something like pressure and temperature and so forth. So how do you define temperature of a single atom? Well, the extension is, I guess it would be the average of V squared or something like that. And pressure would be the average force that this atom imparts upon its boundary. But when you think of a single atom ideal gas, you can make the connection between these two entropies because the information of this atom is, if it's on the left, it's a 0. If it's on the right, it's a 1. You can make that connection. And then when you initialize a single bit by, say, adiabatically compressing with a piston, it takes k log 2 of entropy to do that. So there's the connection, and Feynman makes it in this wonderful chapter of that. I highly recommend, like most of his writings, that you kind of dive into it. But entropy is really interesting in information theory because in thermodynamics, we have the super additivity of entropy. That is, the entropy of a big system has to be at least the sum of the entropies of any two subsystems. You can partition it any way you want. And this is it's sort of like a triangle inequality in thermodynamics. But it turns out in quantum information theory, this is beyond Shannon now, there are quantum states where this is violated, where entropy is subadditive. And I'll throw it right out there. I'll give you an example. This is one of the simplest entangled states that you can write down. It's of 2 qubits or 2 spins if you want. And so I'm going to use qubit and spin interchangeably throughout all my lectures. So spin down and spin up, that's the 2-level system. But we have 2 of them, and they're prepared in a quantum superposition of 0, 0, and 1, 1, or down, down, and up, up. Now, this is a pure quantum state of qubit. I should have put an index here, A and B. This is a pure quantum state of the total system A and B. It's a pure state, so it has no entropy. I mean, I've written down the pure state, so it has no, really, there's no more information to be had, so there's no entropy there. But of course, if you partition the system between A and B, operationally, that means you trace over one system. It's no longer a pure state. We write it as terms of a density matrix. It's a mixed state. It's now probabilistic. It's either down or up. It's not a superposition. And so you end up having entropy if you partition either A or B. So therefore, the sum, the right-hand side here is bigger than the left-hand side. So this is an example. If you want, you can cast, I can't prove this, but you can probably cast all the weirdness of quantum mechanics into this law right here. It's the one, there are many ways to do this. This is a departure from classical physics that quantum has. That's one way to do it. And that it connects to statistical mechanics and thermodynamics is very cool. And look, you just had a lecture by David Hughes on the concept of many-body localization. And these are very similar ideas. The idea that quantum mechanics is a closed system. So how can you define thermodynamic quantities? How can you partition and think about these things? And I know he told you a little bit about that. Okay. One other aspect that connects to Shannon is something that was surprising. Again, I'm giving you some high level details on this field of quantum information theory. Many physicists find the idea of quantum error correction to be as interesting or even more interesting than the idea of a quantum computer that can do cool things. I'll talk about that in a minute. But error correction was actually one of the big deals of Shannon's paper in 1948. Not only did he quantify information, he showed that if you have a noisy channel, you can still send information reliably as long as you encode it appropriately. That's called error correction. It was invented in 1948 using classical bits. And it was a little bit of a surprise in the mid to late 90s that it could be extended to quantum systems. So Calderbank, Peter Shor, Andrew Steen, Sergei Bravyi, Alexei Kitaev showed different versions of quantum error correction. And the idea here is very surprising. If you're a student of quantum mechanics, it's very surprising that if you have an error in a quantum bit, so this pure quantum state, alpha 0 plus beta 1, there's our qubit, 0 and 1. If the information leaks to the environment or there's a measurement or something like that, we call that decoherence. We don't have a pure state anymore. It turns out with proper encoding, you can withstand decoherence. And this is an example of a code. It's not a very efficient code. It's a 5-to-1 code. What we're doing is we're moving the information, alpha and beta, into this very funny looking, highly entangled state of 5 qubits. And trust me, these two states are orthogonal. There's no overlap. Remember, 5 qubits, there are 32 basis states. 16 of them are over here, and the other 16 are over here. Okay, so these are orthogonal states. Now, there can still be errors that occur in this funny encoded state, but it turns out that as long as the error is small enough and it only affects 1 qubit, you can recover. And this sort of stands to reason. Let's say the first qubit gets measured. If the first qubit gets measured, there's still lots of coherence here. And there's a separation between these two code words. There's a sufficient separation that if any 1 qubit goes away, you can still recover. And it turns out, as long as you have 1 qubit errors, and you decode it in the right way, I won't get into any details. In fact, I'm not going to talk at all about error correction, really. I may talk about it in lecture 3. But you basically are squaring the error probability. So as long as P is small enough, CP squared is a lot better. Of course, C has to be, that's a prefactor, that better be pretty small. So what's interesting here in the connection to physics and phase transitions is that you win as long as the probability of a single qubit error is less than 1 over C. And again, C depends on the encoding and all kinds of things I'm not going to get into, but it doesn't depend on P. So as long as P is small enough, you can encode and therefore do longer coherent operations, build with a bigger quantum computer, even though you have a little bit of a leak going on. And so that's somewhat surprising. You're not typically taught that. The fact that there's a threshold for quantum error correction is a big deal, and it's very much like a phase transition. You know, if P is big enough, is too large, then there is no ability to do an indefinitely long computation. Okay, so this is again a connection between quantum mechanics and information theory. In a sense, quantum mechanics is extending information theory to not only dealing with entropy in a different way, but now we can also think about correcting. So,
Chris, can I ask you a question here?
Yes, Leo.
Yeah. So one is, this assumes this is true for like optimum error correction, right? Like if you are doing it well. I guess, right?
Yeah. Okay. So it obviously takes a lot of work to make this entangled state. And when you make it, you better not have big errors. I think this threshold includes all the errors of encoding and decoding.
Mhm.
Of course, when you decode, though, you're back to, now you're susceptible to regular old errors. So you're right. It's not, I don't think you would ever use this particular code and ever decode it, because once you decode, you can't have any errors. So it's a little bit contrived. And I think the version of error correction, so there are two ways out. One is you can concatenate it. You can have higher levels of error correction. Of course, it's going to require many more qubits to do that. The other way, and this is very subtle, it's called a surface code. And it's sort of tiling a code over a huge set of qubits, usually in 2D. And this is what Bravi and Kitaev showed. And I think a lot of the solid state qubit platforms are counting on that type of error correction. It's fascinating, and I'm unfortunately not an expert at all on it. In fact, I know very little.
And can you say that, does this formula, is there an analogous formula for classical computer?
Oh, yeah. Yeah. Depending on the code. And what Shannon showed is that you can make C arbitrarily small.
I see.
He doesn't show you the code, but he says it can go arbitrarily small all the way down to 1, I think. I think that's right.
I see. So in that sense, that's the kind of underpinning of the statement that classical computing error correction is easier and more robust, if you wish, right?
That's right. I don't think anybody's proven that C can be arbitrarily small in a quantum system, but that it can be finite and not depend on N. That's interesting enough.
Right.
But quantum errors, there are many more channels for quantum errors, so C has to be bigger. There's probably some high-level dimensionality argument about that. But
okay, thank you.
Yeah, fascinating topic. Quantum error corrections are real. Most quantum information theorists, I mean, this is a huge area in quantum information theory. And it's a beautiful example. If you're an expert in quantum and information theory, people like Peter Shor or David Deutsch or Alexei Kitaev, that you get to enjoy discoveries like this. Okay, I have one more very high-level slide. It's a little goofy.
Chris, just also one very quick question. So when you said the coherence are spin flips, or you are even talking about dephasing here?
Yeah,
or...
dephasing, fine, as well.
Okay.
Yeah.
Okay.
So swapping alpha and beta, and that's a spin flip, swapping alpha and beta. But putting a phase error on here.
Okay.
Yeah, the 5-qubit code will correct any error.
Okay.
If you only have spin flips, you can do it with 3 qubits.
Okay, great.
Or if you only have phase errors and not spin flip errors, you can do it with 3 qubits. Yeah.
Great.
Okay. Most error correcting that's used now, usually you have at least, this has some problems. It's hard to do quantum gates in this basis. So you might need at least 7 or 9. There's a 13, there's a 17 that make it a lot easier to do gates. But the overhead is pretty severe. You need lots of qubits. Okay. So I think of quantum computing as a good news, bad news, good news story. And I'm going to go over it quickly because it's very high level. It's not really overhyped, but it's very general. And let me tell you that if you don't know the field. The first piece of good news is that when you add qubits, you double the size of the Hilbert space that the quantum state can live in. So in a sense, you're doubling the amount of information content in that system. By information content, I mean the number of amplitudes to describe the state. You're doubling it. That's not the same thing as information because you can't get access to that necessarily. That's basically the bad news. But the good news here is that apparently you can do parallel computation. I mean, you can do massively parallel computing. If you want to compute a function on a bunch of qubits, just compute the function in a quantum way, use quantum gates somehow, very much like a classical computer, and magically all of the amplitudes get processed. So if you want to compute a log table or something, you can compute all those logarithms in one step. And of course, with lots of qubits, this gets really big, really fast. You don't need that many qubits to make it impossible to even store all those pieces of information in a classical computer. Of course, the bad news is when you want to look at the result, and of course you have to look at the result at some point, if you have this superposition of outputs, you're going to get a random answer. And you don't know what the answer is going to be. You don't know the input corresponding to that answer. So this is sort of trivial. So the use of quantum computing is not straightforward. You will not be computing one-to-one functions. Right. You're not going to be able to do that any faster than a classical computer, as far as I know. I'd be surprised if anybody ever proved that a quantum computer is inherently faster at computing one-to-one functions. It's because you have to measure them. But the final piece of good news, of course, is that before you measure, you can take advantage of interference. And this is the quantum algorithm. These red dots, these are gates. They push the quantum wave function in very deliberate ways so that you get a massive interference at the end where most of these amplitudes cancel to zero and you only have one at the output. So it's a massive interferometer. A quantum computer is an exponentially complex interferometer. And hopefully what you're doing doesn't require an exponential number of gates, right? Because if you have an exponential number of gates, you might as well just do it on your laptop. So hopefully this is like a polynomial number of gates, polynomial in the number of bits that you have. This is just 3 bits, so there's 8 inputs. And in some cases, when you make a measurement, there's no more entropy here. There's no more randomness because by design, only the answer that was programmed by the algorithm comes out. You don't know what it is until you look at it. When you look at it, it can depend on all of those inputs. And so this is the promise, the promise of quantum computers, being able to change the complexity of problems, maybe making a hard problem easy. And I'm not going to talk at all about number factoring. That's the big killer app everybody talks about. Factoring can be put in this form. Peter Shor showed that 25 years ago. Number factoring can be made easy if you have a noiseless quantum computer. Of course, you have to do error correction in a real system, but it doesn't scale exponentially with the size of the input. So that's sort of a big advent, I think, in quantum information is quantum computing, the existence of interesting algorithms. Now, there aren't many. There are hints, there may be heuristics, but there are very few provable quantum algorithms that are provably better than classical. So begs the question, why is quantum computing of interest to physicists, and especially those that are summer students in ultracold matter? Well, a couple of reasons. One, I've used the word entanglement. You've heard it earlier in the week and last week. I think entanglement is really the root of all the difficulty in condensed matter in many body physics, right? Why don't we understand high TC superconductivity at a microscopic level? Well, the system's too entangled, and we can't even write down a decent ground state of a high TC superconductor because it's too complicated, right? And it's not just condensed matter. I mean, this hits every branch of physics and chemistry that involves many bodies in a quantum quantum sense. Well, the second reason you should be interested is that ultracold matter is actually what we're going to be using to build quantum computers. That's almost certainly true, where we have control over a quantum state, where we can make pure states and encode them. And of course, the final reason why quantum computing is of interest to physics is these first bullet points are really hype. Quantum computers will be used, maybe they will be used for some of these things, but sometimes you hear quantum computers are going to do everything for life. Well, that's not clear at all. In fact, almost all of these, if quantum computers have impact on any of these, I don't know about the last one, making people happy, but they will be used in a heuristic sense. They may give you a better answer to some logistics problem that you can prove is better than anything you could do on a supercomputer. You might not know why, and you might not be able to prove how much better it does. The traveling salesman problem is a very well-known optimization, right? Where you have to visit, say, every U.S. capital, every of the lower 48 states, you visit every capital without repeating, and you visit every capital once. What's the minimum path? Well, that's a very hard problem classically because it's a combinatorial. There are 48 factorial combinations, right? Possibilities of the salesman to make that path. Now, if you somehow build a Hamiltonian that has a cost function that corresponds to this path, It probably has a really small gap to the first excited state. So even if you find the ground state that minimizes that cost function, it might take exponentially long. But you might use a quantum computer to get a better answer than you could classically. And again, you can't prove these things. And that's why it's really tricky to state any of these things with certainty, except the last one. I would say quantum computers their first uses will be used for these many body physics problems, getting a handle on a many body physics problem in a way that you could not do using a regular computer. That's called quantum simulation. And most of us are physicists. I think probably all of us are physicists in the summer school. We should be interested in that. And that there may be machines out there that can help us with even a contrived or esoteric many body physics problem. That's okay. You start somewhere, and then maybe we can hit these other applications. So, quantum computing should be of great interest to all physicists, I think. Okay, so I'm an experimentalist. I actually build small quantum computers. I want to talk about that. How do you do it? Add qubit from qubit, starting from the ground. So I mentioned here that ultracold matter, number 2 here, is the basis for all well-performing qubits. This slide I sort of stole from Science magazine a couple of years ago, where they were surveying the technologies that are interesting to build quantum computers. And they're all either individual cold atom optical systems or really cold solid state individual quantum things. For instance, superconducting loops, when you cool a superconducting system to nearly 0 Kelvin and you make a Joseph's junction, you can store a qubit in a sense, the handedness of the current going through that Joseph's junction. If you isolate a single spin of silicon in a perfect silicon lattice, and maybe you dope it with an extra, maybe you dope it with a phosphorus atom, that can be a qubit. You can think about kind of that electron talking to another phosphorus atom through the silicon C. NV diamond, you may have heard this beautiful atomic-like system in diamond, where you have a vacancy, you rip out a carbon atom in the 3D lattice, and then you put a nitrogen substituted for a neighboring carbon atom, NV, nitrogen vacancy. It turns out that pair in a diamond lattice almost looks like a perfect atom. It's remarkable. Its natural charge state is 1 negative. It has an electron, and that electron looks a little bit like a hydrogen atom. So you can actually think of that being a single qubit. So I call those synthetic qubits. All of them require ultra low temperatures, usually with big dilution refrigerators. And if you want to scale these things up, the refrigerator is going to get bigger. As an atomic physicist, I work more on the natural qubit side of things, where because of vacuum, we don't necessarily need low temperatures. We do cool the atoms down through laser cooling, but that almost comes for free. It's not a refrigerator. It's one of our techniques in atomic physics. So individual atomic ions, individual neutral atoms, and individual photons. These are very promising platforms to build big entangled states and build a quantum computer, build a big quantum simulator. So I'm going to talk obviously about the ions, and you'll see why. The fundamental reason why is that trapped ions have an extra degree of freedom than a neutral atom has. It has a charge. And that allows us to confine the atom without at all disturbing the internal structure of that atom. That's a very clean way to hold on to an atom. Even if the trap has noise in it, the qubit that's inside the atom does not see any of that noise. So a trapped ion is really the most isolated quantum system that we have in nature. And because it's an atom, it has internal structure, and I'll talk a little bit about that. And I've been working on this technology for a long time, so I would say it's the best out there, but it really has the best properties to think about scaling up and building big entangled states. Now, it shouldn't be lost on you, there are a lot of companies here. This row here are all the private and public companies that are investing in these different technologies. Anyway, so this is all pretty well known. And Honeywell, of course, near Colorado, near Boulder, is making ion trap quantum computers, as we are at IonQ. AQT is a small company in Innsbruck, and Oxford Ionics outside of London in Oxford. So it's nice to have that competition out there. So I'm going to now start to, probably for the rest of the lecture, introduce you to the subject of ion traps and how we make entangled states. That's the goal for the rest of the lecture. How do we entangle these ions? And in doing so, we're going to really think about how to scale it up at the same time. Okay. So this is an ion trap. This chip was made at Sandia National Labs. It's sort of an exotic looking chunk of silicon, and it's plated with gold. There are about 100 electrodes here. You can't really see the details. This is exactly 80 ytterbium ions. They're floating above the chip by about 1/10 of a millimeter. And they're separated by about 5 millionths of a meter, so 5 microns or so. So left to right here is about 1/2 millimeter. Okay, and these sit right above that surface. This is a hole. This is a notch in the chip. And I'm not going to talk. Well, I'll talk a little bit about what makes an ion trap. But each atom here is glowing blue because we're shining laser light on the atoms at a particular wavelength that's tuned to cause these atoms to fluoresce, and we're just capturing that light on a camera. Of course, the atoms are very much smaller than these blobs. The atoms are laser cooled to be nearly at rest and to be about 1,000 times smaller than these blobs. The blobs are just the diffraction limit of our optics, a couple of microns, maybe 1 micron or so. Okay. Any questions on this? This is an atomically perfect crystal. It's assembled externally. We're obviously confining with forces. Otherwise, the atoms would want to repel and Coulomb explode. I forgot to mention, this is done in a vacuum chamber. So there's no air to collide with the atoms, or it's very rare when that happens. And so this is our quantum system. We have individual atoms. I'll tell you how we store qubits within them, or spins if you want. I'll also talk about the relative motion of the atoms. That's going to play a very important role.
So is the density, is it approximately parabolic profile, or what is it?
Yeah, I'll talk about that. It's not uniform.
Okay.
The ones in the middle are pressed together. I'll talk about that. Yeah.
And the other question is this the, as I look at it, is this how high above the chip the trap is, or the ions are, or is this just?
Oh, sorry. I didn't give you a scale here. This is about 1 centimeter right here.
Right.
So you can see my cursor. The ions are about right here.
Oh, this is just project. You kind of
yeah. Sorry,
Okay.
It's a fake picture. We blew it up.
Okay. Okay. Thank you.
Yeah, it's very, very small. Okay. But it's 100 microns, 1/10 of a millimeter away from the chip. So it's atomically it's far away. And that's important. These atoms are not part of a surface. They're not part of a solid. They're in a vacuum. So that's what makes them so pure. And they're, of course, the same isotope of the same element. I'll talk about that in a minute. But how do you trap these ions? Well, with electric fields, obviously. Well, not so obvious. If you don't have the background here, you might think, well, okay, let's just make a force field that points inward everywhere. Unfortunately, we have to do it in 3 dimensions. And that's usually when I have undergraduates come through the lab, that's like the first test. How would you trap a charge? You really want the force field to come inward everywhere, right? And the analogy I always use is it's like suspending a tennis ball with a bunch of hoses. Well, if you have 6 hoses, you should be able to hold that tennis ball. But no, the water has to go somewhere. The water is incompressible, so it has a Gauss's law. If the water comes in, it has to go out. So because of Gauss's law, you can't do this. Even, well, in 2 dimensions I'm drawing here. The closest you can do is make this sort of a saddle point. You can make a quadrupole field that points inward in a gradient, and it vanishes to 0, then it squirts outward. Okay. All right, that's the best you can do. That looks good in the Z direction. You have a nice force field. It's like a spring in the Z direction, but it's an anti-spring in the other dimension. So that's the problem. Looks like I have an animation problem here. I'm giving it up. So there are a couple of tricks that we play in order to make it a 3-dimensional trap. And one of them is to add a magnetic field and we add a magnetic field along the z-axis with a quadrupole here. And so what happens is that this is called a penning trap.
Chris, there is a question. Sorry to interrupt. There is a question in the chat. It says if they are trapped with only fields and they are well isolated, do the ions really need to be that cold?
Oh, no, they certainly don't. But if they're room temperature, they're just gonna they're not gonna form a crystal. This is a classical Wigner crystal here. And if the temperature is too high, then it'll be more like a gas. And so we won't have individual control of the atoms. It'll be like a gas. So you can certainly do that, but you're not going to have individual qubit control.
And he's also asking, it's interesting that the spacing of the ions at the end looks larger than the spacing between those at the center.
Yeah, the spacing is closer in the center than the outside. I'm gonna comment on that in about 5 or 10 minutes. Doesn't have to be that way. Okay. So to trap in 3D, we apply a magnetic field along Z. And what happens is the electric force works in the Z direction. And imagine in 3D, we have an anti-trap along X and Y. That's this quadrupole here, right? We have a restoring force along Z, but a anti-trapping force along X and Y. Well, the magnetic field causes, the Lorentz force causes the atoms to have cyclotron motion. So they never get thrown out of the trap. They just get thrown out and they turn around. Okay, so they keep turning. So a penning trap allows you to hold on to a crystal of ions. They all rotate, but you can put lots of atoms in there. And one limitation is that the cyclotron frequency can be limiting. I mean, if you have a few Tesla, and even with the lightest ion that's used, that's beryllium. And I'll tell you why. Beryllium is the lightest ion in practice. That limits you to of order megahertz cyclotron frequencies. And in practice, it's as you add ions, it gets a lot smaller than that even. So there's another trick I say we use. Well, it's not a trick, it's a technique. And this is what, this is the trap I showed you before. It's called an, oh, sorry, I meant to show you this wonderful picture, partly because Anna Maria is right here. Now, I always show this picture. John Bollinger's experimental group at NIST has worked very closely with Anna Maria and others on wonderful simulations of many body states where, again, a qubit is stored in each atom here. And there's many hundreds of these atoms. And again, when you have many hundreds of qubits, the system can easily be intractable. And so that's really where the interest is. And what's cool about this system is that it's not a gas. It really is a crystal. So you in principle can have individual access to measurements and so forth. So we don't typically make a quantum computer from the ground up using this technology, but we could. And I think that may come in the future. But unfortunately, I think Boulder is the only group in the world that is doing work on this type of a platform. I think most of the others in the world are using another trick. That is, this is called an RF trap or a Paul trap. And the way this trick works is that, of course, okay, we can't have, Gauss's law forbids this, but we can have this saddle point. Well, the RF trap, what it does is it alternates the sense of the quadrupole. So it alternates between confining along Z, expelling along XY, and then confining along XY and expelling along Z. So just put a cosine omega t in front of the electric field. So it's an alternating quadrupole. That's called an RF Paul trap. And so with these traps, you can get very strong confinement. And I want to just go through the dynamics of what that is. It's not always obvious if you haven't seen it. So this is in one dimension, the equation of motion of an oscillating spring constant. So the spring constant is positive and negative. And you might say, well, on average, there's no spring at all. So on average, there's no confinement. Or if in 2D, I actually have a model in one of my labs. We have a saddle point, big plastic smooth saddle point. It's on a turntable, it rotates. If you look at it, you can see that there's, on average, there's no potential and there's no force, but the marble is moving. The marble's moving. You can't average, you're not allowed to, it doesn't matter what the average potential is at any one point in space, What matters is what's the average potential that the marble experiences, and the marble is moving. So the way you do the time average is important. And in plasma physics, this is called a ponderomotive type potential. You get a time average potential. And to see how that works, well, you can also look at this. If you look in Abramowitz and Stegun, you'll recognize this is a Matthew equation, and it has regions of stability as long as kappa is small enough. So when you look at the trajectory of this Matthew equation or a marble on a spinning saddle point, you're going to see this sort of secular motion, this slower motion, but then you see wiggling of the driven motion of the rotating saddle. That's called micromotion. It happens at the drive frequency, but you get this non-trivial secular motion frequency, and this is the effective ponderomotive potential. That, again, we're borrowing terms from plasma physics. That stands to reason, right? This is a one-component plasma. Okay. So the RF trap is what we typically use in quantum information applications, notwithstanding the Penning trap. So when you go in 3 dimensions, it's very easy to make a 3-dimensional quadrupole. This is a 3-electrode trap, and it's a little hard. You have to imagine this is a surface of revolution along the z-axis. So we have 2 end caps on the plus z and minus z axis, and we have this donut in the middle, this hollow donut, and the electrodes are made hyperbolic so that it follows the form of a hyperbola, and we can simply write down this is the exact equation of motion then, because it's a perfect hyperbola. And this is Wolfgang Paul's Review of Modern Physics paper. This is his Nobel Prize lecture. In 1989, he and Hans Dehmelt shared the Nobel Prize basically on this technique. Norman Ramsey had the other half based on his method of separated oscillatory fields that we use to study the coherence of qubits. So here is the Abramowitz and Stegun form of the Matthew equation. We can add a static term here, but the interesting term here is the oscillating one. There's a little Q parameter that we usually denote there. And this is right out of Abramowitz and Stegun, actually, these curves. There's regions of stability in the Q parameter and the A parameter where the motion is stable. And I wanted to point this out because Paul's Nobel Prize was really for the mass spectrometer. And the mass spectrometer relies on operating, I hope you see my cursor. The mass spectrometer operates right on the tippy point of this stability diagram, very sensitive. If you change the mass of the ion just a little bit, it's no longer stable. You're off the stability diagram. So this device can be very sensitive to the charge to mass ratio. So if you make singly ionized ions, you can measure the mass very precisely using this technique. And you can buy these now. They're called mass spectrometers. All the vacuum companies make them. And if you want to detect the mass of the gas in your analyzer, you ionize it, and then you send it through this device and see if it stays trapped or not. And if it doesn't, you can collect the charge. Okay, that's how that works. Right. You notice he says neutral particles in the title here, electromagnetic traps for charge or neutral particles. If you're used to the concept of a dipole trap in neutral atoms, the RF trap actually is a dipole trap in the far blue detuned limit. It's never said that way, but it is. So dipole traps are actually not new. They were, kind of invented back in the 60s, but not using lasers, using RF. Okay. So here's another picture of a realist. I'm getting more realistic on you. These are not real hyperbolas. But if the ions are in the middle of the trap, who cares if it's hyperbolic or not? If you're only in the middle, everything looks, everything is harmonic in a way. So you can use just the lowest order terms to trap ions. If you're going to make a mass spectrometer, you really need them to be hyperbolic, because you don't want anharmonicities to cause dispersion here. That will degrade your mass detection. Here's another even more realistic picture of a trap. This is one of the first ion traps I ever made. It's just a piece of metal with a hole in it, and then another fork that goes around it. And we have put RF radio frequency voltage on the hole electrode, and we ground the other one, and we stick it in a vacuum chamber, very crude, and it works just great. You can trap ions there. The problem with this type of trap is there's only one point in space in 3D where the ions want to be. And again, imagine a spinning saddle and you have repelling particles. They both want to be in the middle, but they can't. So they bounce off each other. They have this driven motion, this micromotion. That's a real problem. So there's a hybrid type of an electric trap that we use whenever we make RF ion traps. And it's called a linear trap. Here's how it works. Now imagine applying a two-dimensional quadrupole. So we have 4 rods and they extend in one dimension, say for a very long distance. And we apply radio frequency to opposing rods and we ground the other 2. That creates an electric quadrupole in the radial dimensions. Of course, there's nothing in the axial dimension. In fact, the ions in the middle will just leak right out, okay? But they will be confined along X and Y, and they'll be confined with this ponder motive frequency. I think I had an equation for this before, not in exactly these terms. There's the little Q parameter I talked about. And R is the distance to the nearest electrode. There's usually an extra geometric factor here because this only works for a hyperbolic electrode and these aren't hyperbolic. So there's sort of a geometric fudge factor. You can look them up in tables and so forth. Lots written about them. They're not very interesting. So there's some correction factor in here, but the scaling with voltage and charge and mass and distance is important. Okay. So we want, in quantum mechanics, we always want frequencies to be big. Why? Because we want their quantum states to be highly resolved. So we want this number to be big. We want a lot of charge. Well, our ions are going to have one positive charge. And I'll tell you why in a while. We want lots of voltage. Of course, whenever you have voltage, you want a lot of voltage. We want light mass, and we want a small trap. So we can sort of have control over these by choosing the right atom. That's why beryllium's great. It's such a light atom. You don't need so much voltage to trap to the same degree of confinement. Now, what about the axial motion? You put a bunch of ions in this trap, they're not confined at all. Well, we can just add a static potential along the axis, and it's just going to be weak. It's going to be very weak so that the anti-trapping, the static anti-trapping that must be there is totally overwhelmed by the ponder motive RF part of the trap. Okay. Now the axial trap is going to be weak because we want a line of ions and we want that crystal. We want the weak axis of the crystal to be along that axis. And by the way, there's no micromotion problem because there's no RF along that dashed line. There's 0 RF motion. So you can now, at least in one dimension in space, hold on to lots of ions and they don't bump into each other and have all this micromotion. So this is called a linear trap. It's the basis pretty much for all ion traps, most ion traps used in quantum computing. Okay. Here's a picture of a real one. Two of the electrodes are hidden. This is a 4-rod trap. There's 1, 2, and there's 2 right below it. They're blocked. And you see these 2 needles. These are end caps. The needles have a static potential on them, and the ions sit right in the middle there. Now you can make all kinds of geometries. The 4-rod trap, you can make 6 rods, and it doesn't really change anything as long as you bias them in this way. And you can clearly go from this geometry to this geometry. Why did I do that? Well, this geometry is maybe a little easier to make because you can make it using wafers and holes and so forth. And in fact, that's exactly what this is. This is a trap that, in fact, in one of my labs, we've been using this trap for over 12 years. In the last 10 years, we haven't even opened vacuum. We had to open vacuum when I moved to Maryland because we were switching atoms. We had to get a new source of atoms in there, but it's been closed up ever since. And we've been running quantum simulations on up to 50 or so ions in this trap. It's a linear trap. If you look very closely, it only has 3 segments along the axis, plus, minus, plus. That means that the axial confinement is parabolic to lowest order. And as was hinted earlier, when you have a parabolic confinement along the axis, the ions will not be spaced uniformly. The ones in the middle are closer together. It's the price you pay. for simplicity. A more futuristic geometry takes the 4 rods here. So this is a picture along the axis of these 4 rods. The red ones are RF high and the blue ones are RF ground, or the other way around. It doesn't really matter. And we move them like this, and then the RF null, the axis where there's no RF field, it lifts up out of the plane, and we have planar electrodes. They're all in one plane. And what's cool about that, of course, is you can think about fabricating this much, much easier using lithography and so forth. So you've probably heard the term surface trap. That's what this is here. You need at least, you could probably get away with 4. I think there's a way, but you typically have at least 5 rails. And I said, let's say the blue ones are RF high, the red ones are RF ground, but they hold static voltages, and the red ones can be segmented along the axis. And now if I take you back to this, this early picture of the Sandia trap, that's exactly what we have. You can't see here, but there are 5 rails, and one of them is segmented 100 times, 50 times. There's 150 on each side. So there's about 100 electrodes here.
And this is a planar one, right?
Say it again.
This is a planar one.
Yes.
It's a planar. Okay.
Planar trap.
Yeah. Cool.
And so there have been, so obviously what's great about these planar traps is that you can use a lot of the lithography tools that have been used for silicon and so forth. And a very subtle reason planar traps are interesting is that, you know, if you have the trap even like this is not a planar trap, by the way. This is that's a picture of this trap here. If you want lots of electrodes and you want to control, say, thousands of ions with thousands of electrodes, you have to wire them up. And if you wire them up from the side, you have you kind of have a fan-in problem. With surface traps, you can wire them up through the device itself, through vias. You can send control voltages right through the bottom. You sort of have an extra degree of freedom. Now that really hasn't been put to use too much yet, but that's something that's important in the long haul. And now a very subtle thing. When you do RF traps, you become sort of an RF guru. You have to know your RF, and high frequency E&M is easy. It's optics with mirrors. Low frequency is easy. It's DC, wavelength's huge. RF is really hard because the wavelength is about the size of your equipment. So you have impedance matching and all that stuff. And what happens here is that when we have an RF, high voltage RF, and we want these to be an RF ground, you worry about stray capacitance. So the RF voltage here is impressed upon this because there's capacitance. So you have to have a very large capacitor from all your static electrodes to ground. And by doing this on a chip, on a surface trap, you can sort of you imprint those capacitors. You can fabricate them. Okay. Right here. Yeah, sorry. I had a little cute animation to tell you exactly show exactly what I just said there, right? When you have this high voltage RF, it will induce itself onto all the electrodes unless you short that RF with a very high capacitance that's much bigger than the trap capacitance between electrodes. This is usually a couple of picofarads, and this one here is usually a couple of nanofarads, a couple hundred nanofarads. So you can really kill the RF voltage there. Okay. So here's pictures of lots of traps, surface traps and others from different outfits. Dave Wineland's group at NIST in Boulder had a very complicated racetrack trap. This is the Sandia chip. I showed you that already. Georgia Tech has built many. Honeywell got in the game a few years ago, and even our company IonQ. We don't fabricate these. We farm every piece of it out, and we package it in the company. But Sandia, I would say, really has taken the lead at making these fantastic traps. So there's the trap. I talked about the trap. I'm done talking about traps. Now I want to talk back about spins and entangling spins. What about these atoms? Well, I mentioned the qubit or the spin is inside the atom. what atom is appropriate here? Well, we're going to be doing laser cooling. So we want a pretty simple atom where we have simple electronic transitions. So if you're working with ultracold neutral atoms, you typically work with the alkali atoms, lithium, potassium, cesium, and so forth. Maybe a few of the alkaline earths, you have a 2-electron system. We like to work with the alkaline earths because we're gonna ionize the atoms once, and so beryllium is going to have 1 outer electron. Same with magnesium, calcium, strontium, and barium. Radium we don't talk about because it's radioactive. It's a pain. But also zinc, cadmium, and mercury. If you look at their electronic configuration, they have 2 s electrons. When you ionize it once, you have 1 s electron. So it has sort of a hydrogenic spectrum. And also ytterbium. If you, I wouldn't have guessed this, but when you look at the electronics, there's a 14 f electrons here, and there's 2 s electrons.
There's a question.
Yeah.
Go ahead.
Sorry, I have a question. Sorry, I have a question regarding the traps. So just a clarifying question. Is the reason you have this lattice along the direction of the trap, is the reason the Coulomb repulsion between different ions that you have, or is there?
Well, oh yeah. I should have said this at a high level. Clearly the ions repel each other. That's why they're spaced, but they're pushed toward each other because we have an external confining potential. That confining potential is very weak along the axis compared to the other 2 dimensions. In fact, the other 2 dimensions are sort of frozen out, if you want. They're much higher frequency. Now, if you pack more and more ions in this trap, eventually they're going to buckle and form a zigzag and then a spiral. And then if you keep packing, or if you squeeze the end in, they're going to buckle, and then you'll get a 3-dimensional crystal. But remember, only the x equals y equals 0 axis, the z-axis here has no micromotion. So if you do zigzag or form a 3D crystal, it's a mess. They're very hot and there's micromotion. So we like to form a linear 1D crystal locally. I mean, you can make this into a large ring if you want, or you can make it wave around. As long as it's locally 1D, then you have good performance. But by design, we make the z-axis trap very weak so that we can make this line. Okay.
Thanks.
Okay, so these are the typical atoms we use for ion traps because we can laser cool them. They're alkali-like. And there are 2 flavors of qubit or spin that we encode in a trapped ion. The one you might know a lot about are hyperfine levels in the ground state, and these are also featured in cold neutral atoms quite a bit. We can use 2 of them for our qubit or our spin. And of course, their coherence time and their decay time is essentially infinite. Even the coherence time can be essentially infinite if you choose m equals 0 states, like atomic clock states, for your qubit. The other flavor of qubit, most ions actually have a low-lying d state. The first excited state is not p, like in some of the other atoms. Beryllium, magnesium, mercury, and cadmium, and zinc. Their d states are higher. But for these 4 atoms, calcium, strontium, barium, and ytterbium, the d state is actually lower, and it's metastable. It can only decay via quadrupole radiation, and you can have a sizable lifetime. And so you can store a coherent superposition between S and D. Now, there are other ions that have intercombination lines. These would be 3-electron atoms, like aluminum. If you ionize aluminum once, you have 2 electrons, and you have an intercombination line. And I'm sure Junyi told you all about the wonderful features of intercombination, singlet, triplet states. We don't do that much in ions. There are some atomic clocks, aluminum, thallium. Let me go to my periodic table. Yeah, all these guys: boron, aluminum, gallium, indium, and thallium, and lutetium. Right. There's one more, lanthanum, I think, has that too. Anyway, so in all the work I'm going to show, we actually don't use this kind of qubit. This kind of qubit is really hard because you need to drive it with a radiation field that will imprint the phase on your spin. And that radiation field is going to be a laser. It's going to be optical. So you have to have beautiful optical control of your laser to think about using a coherent superposition here. Now, Junyi does this. Many people do this. Actually, Rainer Blott's group at Innsbruck, the ion group there, they use calcium S to D for their qubit, but it's really hard when it doesn't have to be. We tend to favor hyperfine qubits that have a microwave gap, and I'll tell you why and how we manipulate these states. So how are we doing on time? So we have another 15 or 20 minutes or so before questions, right?
Yeah.
So I'm gonna talk about ytterbium. This is the ion of choice that I've used for a long time, and there are two interesting reasons. One of them is that the nucleus of 171 has spin 1/2, so it's a simple spin, and that means that the ground state is just like hydrogen. Of course, the nucleus of hydrogen has spin 1/2 because it's a proton. So ytterbium, the ground states of ytterbium look a lot like hydrogen. The frequencies are different. The hyperfine splitting, instead of being about 1 gigahertz, is 12.6 gigahertz. Actually, we know this number. It's a constant of nature, and it's the splitting between the 1, 0 and the 0, 0 state. These states have no Zeeman shift to lowest order, so they're very good qubits. They're not sensitive to magnetic field noise. So this is where we're going to store our spin, or our qubit, if you want, our 1, 0 state. The two other states here, we don't typically store information because they are sensitive to magnetic field. Is there a question?
Yeah, there's a question in the chat about S to D transition being dipole forbidden.
Yes, exactly. The S to D is dipole forbidden. So that you can drive this transition at all relies on a quadrupole moment between S and D. So a dipole allowed transition is proportional to the electric field of the driving radiation, like the laser beam. A quadrupole transition requires an electric field gradient. So therefore it's higher order. It's a higher order process, and it's much weaker. And that's also why it doesn't decay as fast. You learn this in quantum, I guess you learn this in your fundamental quantum physics, right? Fermi's golden rule is only connecting, say, between the two states of opposite parity. But this is a delta L equals 2 transition. And it's a very weak transition, but you can still drive it optically. It has its own selection rules.
Great, thank you.
Okay. Okay, so here's the ytterbium qubit. And the first thing, before I talk about how we make coherence and entanglement between multiple qubits, the first thing I want to talk about is initialization and measurement. Well, initialization is pretty easy, actually. I don't think I have an animation to show it, but we always initialize in spin down. And we do this through a process called optical pumping. And for that, we send radiation in that couples this state to the excited state here, the 1, 0 state, and the 1, 1, and the 1, -1. Sorry, I should have put an animation in here for that. And what happens is this red dot goes up to one of these 3 states, and it can decay to any one of these states down here. When it decays to the spin down state, it stops because there's no laser that's going to get out of there. But if it couples to any one of these 3, the same laser will keep exciting it until it decays to here. It takes only a few cycles, a few tens of nanoseconds for that to happen. And then the atom is in this spin down state with very high probability. It's very hard to measure how high that probability is. It could be 5 or 6 nines, 99.9999%. It's very good. So optical pumping is a type of cooling of the spin. And it's very efficient due to these selection rules and the fact that we have a hyperfine splitting, right? This 12.6 gigahertz is much bigger than the line width of this excited state. So this, when you're trapped in this spin down level, you're 12.6 gigahertz away from a 20 megahertz line. So you're really far away. And that's why optical pumping works. A little harder is detection. How do we detect the state? Let's say we're in one of these 2 states, we don't know which one. How do we detect it? Well, here we apply light at a particular wavelength. It's actually in the near ultraviolet, and it has 9 digits of accuracy. We know what that is. And this is a so-called cycling transition. This, the 1, 0 to 0, 0, it can only decay back to the 1, 0. Actually, it can decay to 1, 1 and 1, -1, but we can clean that up with 2 extra purple beams. Okay, so here we shine light on this transition, and it doesn't decay to the down state. So we get sort of an amplification here. We get lots and lots of photons, even from a single atom. This is real data here on the right. We had a single atom in the trap. We prepared it in the state up, and then we turned on this light. It was tuned just right, and we collected a lot of light. In fact, this is an experiment repeated many hundreds of times, and we have a distribution of fluorescence. The integration time was 50 microseconds, and we collected roughly, on average, 30 clicks. So, every microsecond or so, we get a click. This is a picture of that same atom on a TV screen, just one atom. It's bright. The important point is that if we're in the, I do want to go through numbers here. The line width's 20 megahertz. That means in angular units, it's 2 pi times 20 megahertz. So that sets the scale for the decay time, which is on average about 10 nanoseconds. So the atom emits a photon every 10 nanoseconds, and we get a click every 1 microsecond. So we're only collecting 1% of the light. That's okay. We're not collecting all the light because we just have a little small lens in front of the, we have 1% light collection, and the detector, we have about a lot of numbers here. We have about 5% light collection and a 20% detector. So it's, the optics isn't great. The detector isn't so great. So we're only getting 1% of our emitted light to result in a click. But we get a nice healthy histogram here. And the important point is, if the atom were in the other state, we get nothing. That's the important point. And this is real data. We prepare an atom in the state spin down. We see background counts, noise, cosmic rays, whatever. But the atom really doesn't, it pretty much produces either 0 or a little bit of dark counts in the detector. And the important point is that's a far cry from 30 clicks, right? My colleague Jungsang Kim at Duke has gotten even better results. He gets 99.93% resolution in a single shot in only 12 microseconds by using a better detector and better optics. But the point is, in a single shot, you can tell whether a single atom was in spin up or spin down with very high efficiency, okay? So it's a near perfect detector. Now you might say, well, how good does it need to be? 99.93 is not perfect. Well, if you only have 1 qubit, who cares? If you have 10 qubits, you only need 90%, right? Whatever, 92%. So 99.93 is going to be sufficient for 100 qubits. So we don't need to work on that anymore. Rainer Blatt at Innsbruck, I think he's shown 99.996 or something. That's because he has an optical qubit and you can get better resolution, better discrimination, okay? So we know how to get many nines in detection. Okay, so there's detection, initialization. Now we want to talk about the more interesting part, and then I'll close it down before next lecture. I want to talk about how we entangle and make coherent states of these qubits. We could do this with microwaves, right? Just shine microwaves at 12 gigahertz, and you can make a superposition, just like NMR. Actually, this is NMR at a single atom level. We don't do it with microwaves very much because we actually want to entangle atoms, and we're going to entangle atoms based on their motion. We actually want to apply a force to the atoms while we flip the spins. And we're going to do it exactly like we do with tweezers, optical tweezers in neutral atom systems. We're going to apply a dipole force. So for that reason, to make coherent states of our spin, we use something called an optical stimulated Raman transition, a 2-photon transition. We shine 2 lasers in, and their beat note is tuned to be right next to the hyperfine splitting here, 12.6 gigahertz. But each one of these lasers is really far away from the excited state. And here you can see the real benefit of ytterbium. The fine structure of ytterbium is huge. The fine structure of ytterbium is 10 to the 14 hertz, 100 terahertz. That's almost 1/10 of the optical wavelength here, right? So fine structure in these heavy atoms is really big. So that means we can detune really far and not have a cancellation. This is a little bit subtle. I didn't want to get too much into it. I probably won't. It turns out the best thing to do is to tune in between the two, the D1 and the D2 lines. That is the P1 half and the P3 halves. And the reason is if you tune outside of them, they have a destructive interference. But if you tune inside, they constructively interfere. And so you get a much bigger coherent process, okay? So having atoms with a big fine structure means you can detune far and therefore not have direct coupling to the excited state. Note, this is 33 terahertz, right? The line width is 20 megahertz. That's 1,000,000 times bigger. So we're 1,000,000 line widths away. We're very far detuned. Now, if you ask me why we use ytterbium, I would answer two reasons. One was that the spin 1/2 nucleus is simple. The other answer is an engineering answer. The other answer is that the optimum wavelength to do this stimulated Raman transition, it turns out it's 1/3 of the way between D1 and D2 lines as I've drawn. The optimum wavelength is 355 nanometers. And if that doesn't affect you, 355 nanometers is a commodity. You can buy that. That's what's used for lithography. You can buy as much power of 355 as you want. If you go to Lawrence Livermore Lab and you look at their nuclear fusion, their laser fusion laser, it's 355. Okay, it's UV. It has a lot of energy per photon, and it's the third harmonic of a YAG laser, actually. And so this is a laser that's been engineered to the hilt. And this is a picture of the one we use. It's not like Livermore's laser. It's only a couple of watts. It only has one adjustment, and it's the on button. So we love that laser because we don't have to think about it. And this is, I'm prefacing lecture 3 here, which is going to be more about what IonQ does. IonQ doesn't do so much atomic physics anymore. We don't want to be inside lasers, right? We use atoms as tools to build circuits to do something that a quantum computer will do. Now, the beauty of this laser is also pulsed. So it produces a frequency comb in just the right way so that we can drive we can have pairs of beat notes that all add coherently. And I won't get into the details how that works, but we don't have to generate the two beams. They come for free in that laser. We do have to control the repetition rate, the comb spacing here. Not to the extent that Junyi does, and you saw in his lectures, but because this is we're going up and down, so we don't need to stabilize the carrier phase envelope. You know what that means now. We don't have to do that here, but we do need the beat note between two comb teeth to be coherent, and that's not hard to do. Now, here's the physics of how this works. The stimulated Raman transition is a 2-photon process. You can derive this any number of ways, perturbation theory, other ways. It goes like the product of the individual Rabi frequencies, the individual resonant Rabi frequencies, divided by the detuning, in the limit that the detuning is large. And then this allows you to calculate the error due to scattering. What's the probability that we actually populate this state? I said it was really small because we're 1,000,000 line widths away. And we can calculate this. This is the tail of a Lorentzian line shape, and we're really far away. And if you plug in the math for roughly equal powers on the two beams, you find that the ratio of the bad stuff, the scattering, to the coherent stuff, there's a prefactor here, factor 10 or so, depends, there's 2 pi's and stuff like that. It's roughly 10 to the minus 5. In other words, if you want to do this with the 355 laser, it's going to work really well. You're going to have to do this 100,000 times before you see an error on a single atom, okay? So it's very clean. Okay, this is data from a really old experiment, but it's actually kind of cool. It combines almost everything I said. This is going to show a single qubit, both the high fidelity of measurement and the coherence. So this experiment is very simple. Put a single atom in the state 0 or spin down, turn on this light for a certain amount of time, and it should Rabi flop. It should drive coherent transitions between down and up. It's done in the dark. This is a coherent operation. And then stop, and then measure the qubit. Now, we have near perfect measurement here, so we only have to measure it once. It's like looking at a coin. Is it heads or tails? You don't have to, you don't have, you just measure it once. Of course, if you measure many times, you're going to see dispersion, but you only get one answer. Is it 1 or 0? You don't get a half. You can't measure a half here. You can only measure 1 or 0. And we measure basically the brightness of the qubit. Is it bright or is it dark in a single shot? And we vary the time of the application of this laser beam, which is the Rabi frequency parameterized by theta. And here's the data as it comes in. This is what it looks like. This is Rabi flopping. You probably thought Rabi flopping was a sinusoid. No, this is Rabi flopping with perfect measurement. You see, we know we're in the state 0 at time 0. There's no uncertainty there. Theta is 0. We're always in 0. When we drive a pi pulse, oh no, did I miss a factor of 2 here? Yes, I did. Don't write this equation down. That should be theta over 2, excuse me. And that should be theta over 2. When theta is pi, that's called a pi pulse. We should have driven 0 all the way to 1. Sorry, I can't lecture with bad math. I'm just going to stick it in right now if you don't mind. Okay. Corrected slide.
So
when theta is equal to pi, we're in the state 1. There should be no noise. There's a little bit of noise. When theta is equal to pi over 2, that's when that's the interesting one. When theta is pi over 2, we've made a superposition. It's like an even coin. Well, we see half the time 1, half the time 0, and you can sort of see that. There's noise. No noise, noise, no noise, noise, no noise, noise. So as you go forward in time, the signature that you have a quantum bit is the modulation of the noise, right? Now, if you average, instead of measuring the qubit once, you repeat the experiment a zillion times and you measure the qubit, this is what you get. Of course, you can measure a half when you've averaged many runs, okay? So this is kind of neat. It's kind of trivial in a sense, but it shows that you have both really good measurement and really good coherence. Boy, I didn't get as far as I wanted. I didn't even talk about entanglement. That gives me lots of time tomorrow. It's important to talk about entanglement, and then we're gonna exponentially ramp up and talk about how entanglement can be used for simulations and also for quantum gates for quantum algorithms. So why don't I give up right then and take any questions?
questions?
I had a question. How do you apply like a sigma z field so that you can maybe rotate this x state to a y state, something like that?
Oh, many levels of that. I sort of lied when I said that there's no Zeeman shift. Well, I showed you that, so you know what the Zeeman shift is, right? The m equals 1 states and -1 states are shifted linearly. Well, it turns out there's a very small quadratic Zeeman shift to this level. There has to be. It's really small. We can make that controllable. But by changing the magnetic field, the real magnetic field, we're changing the qubit splitting. And that's a sigma z operation on the Hamiltonian. That's one way to do it. In fact, we never do that. We never change the magnetic field because it hits all the ions. We might want a z shift on just one ion. So for that, we actually use an individual laser. We don't drive 2 of these lasers, but we turn one of them off. And what happens is we get an AC Stark shift, a small AC Stark shift. It's localized, it's controllable, and that's how in practice we get a Z operation. I'll talk a lot about that probably in the next 2 lectures because that's an important tool. Because I'll show you that our native interaction is an XX Ising interaction, but it's XX. So we often want a Z field to be transverse to that and to study phase transitions and so forth. But very good question. Yeah, we've sort of designed our system to not have any Z fields available. Remember I said, we have a very stable qubit. Well, with control comes noise. So you have to open up the door in some way. In this case, either with a magnetic field or a laser beam that will shift the energy levels a little bit. Thanks.
Why is it that you only work with atoms which are ionized once?
Yeah, boy, I realized all the things I wanted to say I never did. You might ask why, what's wrong with magnesium or cadmium or zinc or mercury? Well, these have very deep UV lines, especially mercury. It's like below 200 nanometers. I mean, it's hard to get lasers to work with. And this is just given to us by nature. Now, you might wonder, well, why are you in the UV? I mean, I just saw these beautiful neutral atom lectures. Rubidium, they have, CD compact disc laser diodes they can use to cool all these rubidium atoms. Well, rubidium being a neutral atom and cesium, the outer electron is very weakly bound to the neutral atom. So it doesn't take much energy to go to the p level. Well, when you ionize a neutral atom and you want to work on the next electron, that next electron is bound a little tighter because of the net charge. So now you need UV. You need UV to get there. If you ionize an atom twice, then you need really deep UV. So that's why. To keep it short, we don't use doubly ionized atoms because the transitions are too much in the UV. They're too blue. We don't have lasers. Another question is, why not negative ions? Oh, negative ions are great because a negative ion, you could use infrared lasers for weakly bound states. The problem is a negative ion, that electron is an extra electron already. There are very few negative ions that have excited bound states. Usually you send a laser beam. I mean, if you look at that negative ion too hard, it dissociates. So most lasers, certainly blue, but even infrareds will ionize that negative ion and you no longer have it. So unfortunately, it's not unfortunate. We're stuck with singly charged ions. Most of them are UV. Ytterbium is near UV, 370. Barium is great. Barium is green, 493. That's a really cool ion. Strontium, 422. Calcium, 397. 280 for magnesium. No. 313 for beryllium. Ugh. Zinc, 206. Cadmium, 214. Mercury, 199. So these are all very deep UV. And here's some little experimental physics for you. I know I'm going forever here. How deep is deep? Well, my answer is usually about 330 nanometers. Why? Because 330 nanometers is about 5 volts, 4 volts, something like that, 4.5 volts, EV. Why is that tough? Well, if you shine a laser beam on a metal and the laser photon has more energy than the work function of that metal, you're going to make electrons. If you have an ion trap and there's electrons running around, that's really bad. So ions that are deep UV, they tend not to work very well. So you want to kind of be in the longer wavelengths. And that's, I think, most groups now, they use either ytterbium, strontium, calcium, or barium. That's pretty much it.
Actually, could I ask a somewhat related question, which is, and maybe the answer is very much the same. If you use singly ionized, zinc, cadmium, or mercury, you don't because of the wavelength. But why don't we see neutral trapping of copper, silver, and gold if their electronic structure is so similar? Is it like vapor pressure or is it wavelength?
Yeah, good question. If you look here, yeah, it has a 4s electron, a 4s electron. It turns out that I think in these sort of 1B metals, that the ground state electron is actually a d electron. So if you, it's a weird, right. The electronics is just crazy. And I think when you excite that d electron, you create a d hole and maybe you produce a p. It's just not a closed transition.
I see.
It's just nasty. I wish I call myself an atomic physicist, but atomic structure is tricky. The way the electrons decide to, that's a many body problem already. You have 79 particles, 79 electrons here. Sorry.
Yeah.
With gold, it's not 79. It's less than that, but you have all these electrons and how they arrange each other is really complicated. So there are very few, very simple ones, unfortunately.
I see. Okay. Thank you.
Chris, can I ask you a question about that? Can you show your energy diagram again, the spectrum? Yeah, I missed again. No, it was a different one.
Oh yeah, this one.
This one, yeah. So the lower levels, the 2s 1/2, the that's the hyperfine singlet, and then the other is hyperfine triplet.
Yeah, I'm sorry. I don't have very good labels here. When I turn in my slides, I'll label these. Yeah, that's 0, 0. That's 1, 0 here. 1, 1, 1 minus 1. That's the FMF basis.
Right. And so can you explain again, like, how do you select the one on which there's, the 1, 0, whatever the one that you're using for upspin, as opposed to the other guys, the other hyperfine spin, hyperfine triplet states? Like, what chooses that? Or is that spectroscopically
Yeah, it's spectral. It's spectral. This gap is huge. It's not to scale. This gap is about 1,000 times bigger than the line width of the excited state.
No, I meant more, but I meant more the Zeeman splitting between the triplet states, hyperfine triplet states.
Oh, those three. Yeah, I see.
Why don't you populate some of those?
You certainly do. In this transition, you populate those.
Oh,
actually, you populate all. Let's see. Sorry, this one can't decay to 0. 0, 0 to 0, 0 is not allowed, but you do populate these. So where I lied is that we actually have 3 beams, and they have different polarizations, and they're not resolved. We don't spectrally resolve them. They're just different polarizations, and they're all driving together. All you want to make sure is that if you're in this state here, you remain dark. That's all. But if you're in the excited state, you need to keep the process going. Now, if you know a little more about atomic physics, you'll recognize that will make a dark state. So that's why the Zeeman shift is important. The Zeeman shift causes the spin to precess, if you want to think of it that way. So that's why the Zeeman shift is important. The Zeeman shift causes the spin to precess, if you want to think of it.
You tune a laser to the readout laser is tuned to the transition you have indicated, but the flipping between up and down, use a different laser to go through the upper state in that delta configuration.
Yeah, that's right. Here, I'm actually animating this a little better so I can put three lines in. Okay, so we do this basically.
Mm-hmm.
You can either modulate the polarization, or with the Zeeman splitting on, that takes care of it. So there's no dark state here.
Right. But then you had this other diagram where you were, which was allowing you to go, no, not this one. You're allowing you to go from up to down.
Oh, okay. That's an off resonant process.
Right. So it's all just you change lasers. So you turn one laser on to initialize or to flip between up and down, and the other one is to read out.
Yeah, this one you have to pay attention to polarization.
I see.
In fact, this has to be sigma plus, and this has to be sigma plus.
Uh-huh.
If you have sigma plus here and sigma minus there, nothing happens. Actually, if you have linear light here and linear light there, nothing happens. There's a little tricky selection rule that happens.
I see.
But if you have linear perpendicular to linear, then it works. Optical lattice people, they know all about this stuff. It's kind of the same thing.
Okay, thank you.
Yep.
Can I ask a question?
Yes.
Yeah, I have one. So when you are, I guess my question is about loading the ion trap. So do you do your photo ionization before you turn on the traps, or do you actually do you make ions and then ramp the field up?
Another great question, because I didn't even say anything about that. So good. And it's funny, in ion traps, we don't think about loading too much, because often you load in the morning and you're set for the entire day, because the atoms stay there. It's not like neutral atoms that they leave every few seconds. So they stay there all day. So the way we load these atoms is we make neutral atoms, and we evaporate them from some source. And that's actually why we have this notch. This is a through hole in the trap itself, and the oven is way down below. So the neutral atoms come through. And we can't shine the neutral atoms from above, because then it's going to short the electrodes. All right. So that's why we have this hole. Okay. So the neutral atoms come through. Of course, they're not ions yet. And as you said, we photo ionize them another laser beam that's tuned to the neutral transition. In ytterbium, that's 399 nanometers. And that drives the singlet P, singlet S, singlet P transition, a very strong transition. It ionizes the atom, and now all of a sudden it's an ion and it's in the middle of the trap. So it's trapped. It's not cold. We have to send another laser beam to laser cool it. I'll talk a little bit about that tomorrow to get all the way to the ground state of motion and so forth. But yes, that process sounds really painstaking and so forth. But once it's set up, the oven is set up, and we flash a little bit of current through the oven to make a puff of gas. We flash on a laser beam, and we make sure that we've loaded these ions. We're all done.
So your RF is already on once, even before you've made ions.
Yeah, yeah. In fact, I will show you in the third lecture an animation from IonQ, real time loading a chain of 24 ions, one at a time. You can't see it, but there's a little tiny hole right here. You see that you might be able to see a Y junction here at the edge here. This is a junction, a trap junction. We can trap ions along the spine and along each branch of this Y junction. There's a little hole. We actually load each ion here and we shuttle it one at a time into the zone where all the other ions are there. And you see them add one at a time, boom, 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 boom. And on the camera, we see them, we get as many as we want, and then we stop. And then we stretch the ion. I'll show you the animation, how that happens in real time. It takes a half a minute.
That's really cool. Thank you.
Yep. Any other questions? These are all good questions, and it'll help me for the next two lectures too. I did try to aim at an appropriate level, and I think I kind of got it, but boy, I missed a lot of things.
In the beginning, you mentioned, I guess, when you showed that science picture, there were different platforms. And
Yeah.
I guess you said ions are probably the best, or maybe going to be the best. I was wondering, like Google went with superconducting qubits, right, for their clever 63 qubit thing. So do you know why, like, is there any advantage, like in the future? Is it going to be?
This is like a syllogism. Google is the best, and Google started with superconducting qubits. So what's going on here? Well, not just Google. I think Google and IBM are both, producing kind of the best type of superconducting qubits. Rigetti is a startup, and they have their own fab, and there are a few other outfits that are doing superconducting qubits. So the question is why? If I claim ions are the best, well, that's complicated. I think partly we're used to the fact that computers are made out of solid state materials like silicon. Okay, a superconductor is more exotic than silicon, but at least it's a chip. At least you can use lithography, and you can imagine how to put 1 million qubits on a chip. I would argue very strongly that the real problem is when you get to scale. You have 1 million qubits. They're all different. They're all man-made. They're all a little bit different. And it's going to be very hard to deal with that. Now, the way they are all thinking is this surface code error correction. And I did talk about error correction, right, for a minute. I'm actually glad I did, because the surface code version of error correction, it's not 5 to 1. It's like 10,000 to 1. You need lots and lots of qubits to use the surface code. But if you're Google, you're not worried about 10,000 to 1. If you need 100 good qubits, then you just make 1 million normal qubits and do it 10,000 to 1 encoding. The problem is, how do you make 1 million qubits? I mean, you need a refrigerator that's the size of a building, a dill fridge, and it's going to cost $500 million for that. So there are issues that I firmly believe are going to make it really hard to scale those systems without physics breakthroughs. So why are Google and IBM doing this? Because they don't know atomic physics, maybe? I don't know. They're afraid of vacuums and lasers, I suppose. It's a cultural thing. And I see it. I mean, certainly on the company side, you see it all the time. We have to find investors for the company. I know it's beyond the scope of the summer school, but you should know this. I mean, the investors, the first question is, how the hell do you think you're going to beat Google? And the answer is they have a blind spot. They have a blind spot. They don't think that atoms scale. These are atomic clocks, though. Yes, they scale. We don't worry about them being different. They're exactly the same. Every one of them. We can make 1 million of them and not notice any difference between all 1 million of those atoms. Of course, we have to hold them, and there's a lot of engineering that has to happen, but they're not physics breakthroughs.
Well, your atoms are the same, but the environment they're in can vary, right?
Not with ions. I mean, if you've trapped an ion at the RF node,
your trap potential is, creating different environment for each of the ions. Like,
oh, the ions at 0 electric field average, right?
well, they're in that trap. That's why they're not equally spaced, right?
Yeah, but they're not equally spaced because they're at 0 electric field. It's like space charge, right? They know the other ions are around. They talk to each other, but they don't talk to the environment. Of course, there are magnetic field noise. The second order Zeeman effect gets in there. You have stark shift from black body photons. Jun Yi is worried about that. We're not worried about that. That's a 10 to the minus 12 effect for our ion. No problem at all. 10 to the 12 gates. That would be great if we could do that. So no, really, that's not what we worry about, the inhomogeneity of the ions. We worry about how do we deal with, shuttling 1 million ions in here and controlling the lasers, turning them on and off. That's a massive engineering challenge. It's not a physics challenge.
How do you connect two traps here? Because that would limit your gate time and fidelity.
Very good question. Very good question coming from an ion trapper. So yeah, indeed, as I'll show in the next lecture, we're not going to be dealing with 1 million ions in one line. I don't see that. So we're going to have some type of a modular architecture. And I'll tell you, the visions for doing that. One of them will involve coupling the qubit to single photons that go to another collection of atoms. Again, this is engineering. All of the protocols for doing this have been demonstrated. They're noisy, they're slow, they need to be improved. But the physics is sort of, we understand how we can exchange entanglement using photons. There's another way to physically move atoms around between zones. You can do that too. Honeywell relies more on that type of scheme. I'll talk about both of those. Good question. It's a good question because we're not going to deal with more than maybe 100 ions in one string. It's important to know.
Well, so I think we're getting pretty late into the day. So maybe this is a good time to wrap it up. Thank Chris again, and we'll continue tomorrow at 9 o'clock. So please get some rest. And thanks for all your questions. Thank you, Chris.
Yeah, thanks for hanging out, everybody. See you tomorrow.
See you tomorrow.